I would like to present you an algorithm for automatic crack propagation model in three-dimensional finite element models. I just 10 minutes, so a very few time. I will try to give you a basic idea about the algorithm. So why I think about this algorithm? The problem is when you are trying to make some finite element simulation of crack propagation, you need to modify the model to accommodate crack propagation. So we can use two different methods. What I call the classical way to solve the problem. At each step of the propagation, you modify the mesh to accommodate crack propagation, and you achieve this using global remeshing, local remeshing, or ad hoc solution. The problem is that your mesh is modified at each step. So how do you deal the problem of transfer to residual stress field of plasticity from one step to the other one? You have to map the solution from one step to the following one. On the other way, you can use, I call it a modern way, you can use example XFEM or cohesive elements and so on, meshless methods. But these are hard to implement from scratch, so you need a solver implementing this solution. And of course, they have some problems too. So what I present is a classical way solution. I propose this kind of solution. Why? Because some years ago I proposed a simple solution for a planar and shell finite element model. Here you see depicted the four basic steps of the algorithm for the planar case. You start with a crack, and the vector in the figure is the modulus and direction of crack propagation in the step. You first select only the elements that are interested by this propagation. You you remove it from the mesh, and you replace using a triangulation algorithm. Then you move slightly away the nodes on the new crack surface in order to open slightly the crack if you want. So the problem is how I can extend this algorithm to the three-dimensional crack front case. The solution comes from the fact that a lot of solutions for the three-dimensional case are based on layered mesh. This is an example for a plate, but they are used also for more complex cases, like this is a pipe. You can see the crack, and if you enlarge the crack, you can notice the layered mesh. Layered means that in the part where crack is propagating, the mesh is repeated by parallel layers. So, how can I extend the algorithm? It's supposed to work only with 3 layers of your mesh. There is a crack, but it is not mandatory. You focus only on one layer, then you work on the 2 surfaces, surface 1 and surface 2, and apply the same algorithm for the bidimensional case to these surfaces, and you obtain the new, you substitute the original element that are cut by the crack propagation using triangles. Then you connect these triangles on surface 1 and surface 2 with 3-dimensional elements. And you repeat this process for each layer, but each layer is independent from the other one, and the crack direction and modulus of propagation is different from each layer, so it's a generic application. Then how can you evaluate the stress intensity factors with some algorithm, with accuracy I mean? I use a submodel, finite element submodel, with a focused mesh on the crack front. I adopt the quarter point technique to obtain quite accurate results also with coarse mesh, and then I decided the crack propagation direction at each step using this submodel. But there are some problems for accuracy. I will show you these problems using a really simple example. This is a set specimen using for fatigue testing. This is loaded by a bending moment. I use this configuration because in literature you know the solution. This is the solution for the KIF P1. So this is the deformed shape of the specimen. I started from an unnotched specimen, then I created the notch you can see here using the algorithm. You can notice the triangle elements that are created near the crack faces. Okay, so this is the result the first problem of accuracy is the accuracy near the free surface of the model. You can see this is the value of the key 1 for the thickness of the specimen for different crank lengths. And you can see that on the free surface there are first these peaks in the key 1, then key 1 drops suddenly. And you can't explain this behavior. And so how can you achieve a better accuracy? This is the result. You can see that the fact that the key 1 drops suddenly on the free surface generates very slow crack propagation rates on the free surface. And this is not really true, because if you check the angle between the crack front and the free surface, I obtain 25 degrees in this case. The theoretical value is about 11 degrees, because this was a titanium alloy. So I propose this correction that other researchers used in literature. You can explain this strange behavior because near the free surface you are no more in a plane strain condition, but you are in a plane stress condition. So I modify the last values of Q1 using a plane stress condition. And you can see that you have no more the peaks near the free surface. But still, the value in the free surface is really, really low. So the second correction I apply to the model is to extrapolate the values on the free surface starting from the center of the thickness. And this is the propagation using these two corrections. As you can see, the crack front is better now, and if you check the angle between the crack front and the free surface now is 8 degrees, more or less, and as I told you previously, the theoretical angle is 11 degrees. So it's a quite good result now. The second problem for accuracy is what I call element row shape. What I mean, due to the way the algorithm works, the crack front must always be contained inside one single row of elements. In this case, for this figure, is one single line of elements. You can see that here, if I can get the mouse, okay. You can see that these crack fronts are all contained inside this row of elements. The red line is the next crack front evaluated by the algorithm, and you can see that this line crosses the edge between two rows here and on the other side. So this is not possible. You can't handle this with the algorithm. So you must make an artificial advancement of the crack, and this is the situation here. So I add an artificial advancement to the crack. But what is the result? That the accuracy is really, really low. You can see here on the left the cross-section of the specimen. You can see that the first fronts are okay. Then you must add artificial. I should come back. You must add artificial advancement to the crack, and you obtain that crack from here starts jumping only one crack front for one row. And the crack front can't evolve the shape. This shape is not the correct one. Here are the values compared with the one in literature. You can see here the error rises really high. So how can I solve the problem? I have to adapt automatically the shape of the row in such a way to merge the shape of the crack front. You can see that here I started with a straight row of elements, then the algorithm modified it. I applied the adaptation till here to check if this is a valid solution. These are the results, but more significantly, we can see the error percentage error. You can see a first part here, the error is more or less the same with adaptation or without adaptation, but the problem here is that the crack is nucleating, so the profile obtained here is not iso-key. So I can't compare it with the results in literature. When the crack front is iso-key, you can see that if I do not apply the correction, the blue line, the error is high, 3%. If I apply the adaptation, you can see that in absolute value, the percentage error is low, 1.5, and you can decrease it with a more final measure. At the end, from 12.5 millimeters, more or less, I stopped the adaptation, and you can see that the error starts rising again. So in conclusion, this algorithm is really easy to implement, it's faster also for large models because it works only on few elements near the crack front, and it can be interfaced with the existing finite element environment. However, it requires a layered mesh, so you must build a layered mesh, and you must implement an adaptation to have high accuracy of the results. I'm working to avoid the layered mesh, so probably I will present something next year.